Today I'd like to talk about Python more. This is a computational mechanics course. It's not focused solely on programming, but we need to do some programming. So as a motivating example, I want you to think about this device right here. So this is what we call an oscilloscope. And if you were taking a lab-based course in physics, you would learn all about this device. You would learn what the buttons do. You would learn how to read the display. You'd learn how to connect instruments, and you'd learn how to make measurements. As you work with the device, you would learn or bring to it knowledge of voltage, current, impedance, and AC and DC signals. And the goal of that lab course would be to learn how to use this oscilloscope. But of course, you don't actually learn how an oscilloscope works when you're using it. We're going to take a similar approach to Python. Our goal here is to learn what we need to know so Python can do what we want. We're not going to try and learn everything. And we're going to try and focus on the essential syntax, the numerical models, and the plots and the animations as outputs. Okay. I'm just going to take a pause here. So someone sent me a message on the chat. In general, if it's not actually private, how about we don't send private messages so everybody can see that very useful question that was just sent? And that's that one there. So what that means to me is I have a feeling it's because I'm trying to talk and record in the same room as that microphone. So, Kyle, what happens when you turn off the speaker on the main part of the room? Okay, can you hear me clearly? To those who are helping me test and listening through earbuds, can you hear me clearly? No, so it's yep from some and no for others. Who's a no? Well, now, so are you using earbuds and can you hear me through that, or can you hear my voice echoing, reverberating around the room? Okay, and so this is a situation where I can't actually hear you talking. So this is where Kyle comes in. Kyle, what is being said? Right, and Kyle, if you want to open up your microphone on that machine, that could be helpful.
Can everybody hear me?
Yeah, we can hear you, Kyle. Good. So what's the issue? Can people hear or not hear?
With earbuds, can you hear? Yeah? Yeah, okay.
Okay, so for the purposes of going forward, when I'm not physically in the room, I don't think we're going to have an issue with echo. Cross my fingers and hope for that. So Kyle and I will continue to test this after class today. Right now, those who do not have earbuds, can you hear my voice even if you're at the far side of the room?
He can hear from this computer.
You can hear from that computer. Oh, well, there we go. And we solved the reverb issue?
Yeah.
Yeah, like you speak really loud.
Yeah. So we can hear you, but we cannot hear the computer monitor all the way on top.
The expectation here is not to hear the computer monitor today. We've turned off the speakers in the room to avoid the reverb. We got some choices. Do we go with reverb or do we go with my natural voice that you can hear? Voice. Okay. Let's continue and keep on trying here. Oh, more private messages from people. Okay, I'll figure this out. It's all good. Okay, so on to the body of the work here. when we are dealing with Python, we're not going to try and be Python experts, but we are going to try and focus on some syntax, that is the language, so we can do numerical models, and we're going to be able to make some plots and animations. Those are the goals in terms of how am I going to use Python going forward. In a scientific model, and it doesn't matter what type of scientific model you're dealing with, but we're talking about physics models here, the general pattern is you want to figure out what your model is doing, how it's behaving, and if you can, compare it to an experiment. So if you're looking at any physics problem that you want to numerically model, one of the first things you want to do is just understand that model that you've come up with. Models are used in science all the time. Once you have done that initial exploration, our goals are to verify the model, and that means to compare it with experiment to make sure it works. We probably want to modify and change the model. And then we want to run and do new simulations and experiments. The typical approach is to start off with a set of initial conditions, determine what this model is going to do by simulating it, and then make plots, tables, and animations. Let's make this concrete. I'm going to consider the physical problem of dropping an object, so a falling ball. And let's look at how we're going to model this numerically or in Python. So here's the model. The model is a simple particle model. We're assuming that a ball is being dropped near the surface of the Earth. The ball is only going to fall vertically. It's only subject to the force of gravity. Because you're near the Earth, the force of gravity is constant. For this first go at it, we're going to ignore air friction. And so the only force that's important for a falling ball, a falling particle, is the force of gravity is equal to minus mg. M, of course, is the mass of the ball, and g is its gravitational field, gravitational acceleration, if you will. Physics gives us an equation of motion, something to tell us how all the forces are going to make something work. And of course, you know Newton's second law, force is equal to mass times acceleration. So those two pieces of information, knowing what the forces are and Newton's second law together, give us a model for what a falling ball would be. So we call this an equation of motion, or the numerical model, or the physical model we want to solve. We're not going to deal with A as acceleration. We're going to recognize that an acceleration is a derivative. And so we have the mass times the acceleration is equal to minus mg. This is the standard sort of thing. We call this a second order differential equation. Differential equations are not a requirement for this course. I'm not expecting you have done a course in differential equations, so let's introduce the terminology. Differential equation just means an equation that has derivatives inside of it, and the goal is to try and solve for what this function y is. Y isn't a number. Y is a function, a shape, a curve, a line, some function of time, and we want to determine that. We say differential equations have an order, and that's given by the highest order derivative in the problem. This is a second derivative, so we call this a second order differential equation, a second order DE. Now, you recognize this differential equation. This is what we cover at the beginning of high school, and then in Physics 1050. There is the analytical solution, right? So you'll recognize these as being the kinematic equations. We know that's the answer to this problem. What we're going to do is we're going to use this as a sample problem to understand how to use Python to solve such things and compare back to this as our exact answer all the way through. Okay, so let's rewrite this second order differential equation as a system of first order differential equations. This will be a standard strategy. Anytime you have a higher order differential equation, first, second order, third order, fourth order, you always can rewrite it as a system of equations where all the derivatives are first order. What does that mean? It just means that you, rather than talking about the second derivative of y, you talk about the first derivative of velocity equals minus g, and then you introduce a brand new equation that's very simple. And the equation is the position is equal to velocity. So this turns this equation, which has a second order problem, into two first order problems. That's the first step. Have an equation of motion, turn it into a pair or a triplet of first order differential equations. What we're going to do as we come up with different numerical models is we're going to approximate these derivatives as what are called finite differences. They're approximations. If you remember taking calculus, you would have learned something called a Newton's quotient or a definition of a derivative. And one way of defining a derivative was in the limit as a function at like a plus delta x minus x of a divided by delta x, or x of f of x plus h minus f of x divided by h, or something like that. That was how derivatives are defined in mathematics. What we're doing is we're assuming that delta t is small and approximating this pair of equations as this pair of equations. Now, it's not a perfect, it's an approximation, and it's not exact. In the limit, mathematically, of delta t going to 0, this becomes exact, but we're going to make an approximation so we can solve it. If I take these two equations and rearrange them, I can come up with a rule or an algorithm that lets me figure out what y at a later time, we say y of t plus delta t, is equal to in terms of y and v at an earlier time. So here we go. Y at a later time will be equal to y at the current time plus v at the current time times your time step. And if you rearrange the second equation, then velocity at a later time is equal to velocity at the current time minus g times the time step. This algorithm of using finite differences and evaluating the function at a known time to figure out what it is on the next time step, that's called the Euler algorithm. And it's found using finite differences, where those finite differences are evaluated at the current time, and delta t is called the time step all the way through. So to be able to solve this numerically, what we want to do is we want to follow the value of y and the value of v and look at how it changes in time. We want to begin with some initial value. To start this algorithm off, you need to start with something. You need to know what the position and the velocity is at time equals 0. And then we iterate, which basically means go through this process again and again and again. Theory, and this is what you take if you take a course on numerical analysis, says that if delta t is small enough, the solution of this algorithm will be close to the exact solution. Now, we're not going to do the numerical theory right now, but what we're going to be able to do is test how close this numerical result is to the exact answer, because we know that. Okay, so let's go with this example. Here is an example of a first order differential equation. So this is pure math, no physics here at all. This is the equation of some unknown function y, and the goal is to figure out what y is as a function of x, is equal to some right-hand side. This right-hand side is known when you write it this way. It's some algorithm. It's x squared or x cubed or 2 times x or something. Euler's algorithm says the rule to figure out what y is at a later value is what y is at the current value multiplied by evaluating this function f at that x at the current value times delta x. You should get that from a finite difference. What we're doing is we're approximating the rate of change of y at the beginning of the interval between xn and xn plus 1. So here's a specific problem, and the problem is, what happens if I was to tell you that f of x equals 2 times x, and I was to give you an initial condition at the very beginning, when x is equal to 0, y is equal to 0. Could you do the Euler algorithm and figure this out? Analytically, if I tell you the derivative of a function with respect to x is equal to 2 times x, you should be able to realize that in general, those are functions of the form x squared plus a constant. You just integrate both sides. And then you know that when y is equal to 0 and x is equal to 0, this is the exact answer. So to go through this process, an exercise would be use delta x as 0.1 and figure out what yn is for the first fellow time step. So I'm going to call that the very first assignment question on assignment number 1, which will be due at the end of next week. So take a look at it, work on it in your own time. I'll rewrite this up as an assignment, but the idea is just to work through that, to see what those first few numbers are. And then I want you to make a plot. Make a plot of the difference between the exact solution and the approximate solution given by this Euler algorithm. By the end of this lecture, you'll know how to do this in Python and how to make this plot. There's a question that popped up about, will these notes be on D2L? Well, all of these notebooks are available. I can make a copy of them onto D2L as well, if that's useful. I can do that. The video lecture, copy of what I'm saying right now, will also be available. Is that enough? Is that sufficient, Cassandra?
Yeah.
Awesome. Will this lecture be recorded? It is being recorded right now as we speak, and I will put it up on D2L or a link so you can review it afterwards if you need to. Okay, so that's the idea of the Euler method. What we want to do now is learn enough Python programming to be able to implement this algorithm and solve a falling particle. Now, I'm following this textbook all the way through. So this is the computational simulation methods book that I referenced in the course outline last time. It's all available online. It's free to access, but the authors of that book use the computer language Java. We're not doing Java. We're doing Python. So what I'm doing in this lecture is I've basically taken those first couple sections of that chapter, and we're going to go through it with a different language. So I've rewritten all the parts. It may be useful to browse through that textbook, but don't get hung up on the fact that it's in Java. Almost everything you need, nix that. Everything you need is probably in these lectures. So refer back to these lectures as your primary source of information. Here is an example of a Python program that shows you how to model a falling ball. A Python program, any Python program, it's a sequence of statements where there are variables that are going to hold information, and we have functions that are evaluated and work on those variables. Every statement's on its own line. Python is an example of an interpreted language, which means that it needs to be run through an interpreter, a program which will execute each line. This is in comparison to a language like Fortran, Java, or C that is compiled, which require the code to be run through a compiler. Typically, for Python, the language, you run it through a program called Python, which is, I know, the same word, but that's what they call it. We're using an environment called Jupyter that has built into it a Python interpreter. So whenever I get one of these cells, which is what the thing is with this symbol on the left-hand side, and I get some Python code, as long as I put my cursor inside there and then hold down Shift and then Enter. Shift and then Enter, you'll see that that cell has been executed. There's the one, it tells you it's happened. You have now run some Python code through an interpreter all the way through. And I've given a highly commented example of a Python program, so we can go through all the parts of it to learn how this all works. The first part of the program is the idea of comments. Comments are part of good programming style. They explain how this program is written, why you made the choices you did. This is overly commented. I have put more comments than one would normally ever put in a program. But this very first comment was just to give an example of a comment. Anything with this pound mark or hash is ignored by the interpreter. So it's something that lets you put in comments to yourself or to me. Functions, which are the basic building block of programs, are defined using the def keyword. What you do is you have the letters DEF, short for definition, and you give your function a name. So I'm going to call this my first falling ball application. There's always round brackets after the name of the function, and the function ends with a colon. What you're saying is this function is defined as all of this stuff underneath. There's another kind of comment in Python. Not only can you have things like this, but if you had a multi-line comment, you can use these things called doc strings. Basically 3 quotes, and then anything inside is treated like a comment. So if you ever found yourself in a situation where you wanted to, say, comment out a large piece of code, this is a nice way of sort of commenting out a very large section of code without having to comment out each line all the way through. These doc strings are used for the documentation aspect of Python, which we'll talk about now. Python has a very rich help system built into it. As soon as you define a function, you can then ask for help about that function. If you take any function you want and type in its name, followed by a question mark, and then do a shift return, execute that cell, you get some documentation right away about what that program is. So this is its signature. It's basically what it's called. This doc string simulates a falling ball, uses the Euler algorithm, displays the numeric and analytical results. That's what this stuff is all the way through. So that's how these things get. When you're using Jupyter, you can do something even fancier. If you put your cursor right next to any function and hit Shift Tab, what will pop up is that little bit of documentation for that function. Let me demonstrate this back in the original code. So let's pick a function. So I'm going to pick the function range. There is a nice function. Suppose I wanted to know what range did. What I can do is hold down Shift and then Tab, and what pops up is some documentation. It tells you in as compact a way as it can how to use this program. So there's the basic idea. You either can say range of stop, or you can give it a start, then a stop, and an optional step. And it gives you a 2 or 3 sentence version of what the program actually does. This is a nice way of trying to remember how this stuff works. Shift Tab very quickly brings up the documentation. Finally, built into Jupyter is this wonderful menu option up here called Help. And what it has in here is the documentation. There's tons of it. I'm not expecting you will read it all, but be aware that it is there. So if you're given a brand new function, you're like, I don't know what that does. You can look it up. You can look up how to use Jupyter Lab as an application. You can look about anything in the Python as a language, or any of its libraries that we talk about. So one of the things that we talked about, we're going to talk about in this program is some of the functions. I could click on Python reference, and what opens up is a little web page inside of Jupyter that lets me look up something about the language, because maybe I need more information on the range function. Range, there you go. Beautiful thing about Jupyter Lab is it's supposed to be all-inclusive, so you can take this window, drag it, move it on to the right, and if you needed to sort of follow along some documentation at the same time as following along here, you have that facility within Jupyter Lab all the way through. Okay, so we can look at help all the way through. Python syntax. So when you're looking at a Python program, there is white space. White space are these indents all the way through. They are meaningful to Python. In a lot of languages, white space, the tabs and the spaces are optional. They're just there for make it look pretty. In Python, they said, you know what? Code reads better when it's indented properly, so let's require the code to be indented properly. All of these lines are part of this function because they are indented the same amount. If you ever have code which is indented the wrong amount, so here's this, 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 and this. You see they don't quite line up all the way. See how the colors changed? It's letting you know that something is not right. You need to have the indents always being the same. It's part of the language. Other programs might use braces or some other syntax, semicolons. Python uses white space. In general, you always want 4 spaces for every indent. There's a nice thing that when I hit the tab key, it puts in 4 spaces. Depending on where you're using it, sometimes the tab key actually inserts a tab character and life gets awful. Indents should always be 4 spaces, no more than 4. No less than 4, 4 is the answer all the way through. When we do a function, we say we call it or invoke it. And what I'm going to do is use a convention following from the textbook, that the outermost function, the one that runs the whole thing, that runs the program I want to look at, will always have the word app inside of its name, sort of like a little app you might find on your phone. This outside function is going to drive the whole thing, is sometimes called driver code or target code or the application code. One way to run this program, and this is a conventional way of doing it, is you take the text, you copy and paste it into a file, you give the file a name or an extension with an extension of .py. You would add the line first falling ball app, open and close round brackets, and then on a command line or a terminal, you would type in Python first falling ball app.py, and that would run it through the interpreter. We don't have to do that because we're working within a Jupyter Notebook. And in a Jupyter Notebook, to execute a function, once it's been defined, just means going up to it and hitting Shift Return. Now, there was a question that Sarah asked, how do we know when the function is finished? The function is finished when this number here appears. It takes a moment between when I run it and it appears. If you can notice it very, very quickly, there's this asterisk which appears and then it disappears. When it's gone from an asterisk to a number, it's done. The other signal or hint to use is if you look in the top right-hand corner, which you can't see because of my window, which is my face, which is over the window right now. This is when Kyle jumps up and goes, I should move that. Aha! This little circle right here. Notice when I execute a line. Oh, that program was too slow. Oh, it flashes so imperceptibly. I can't even see it on that screen. But on longer programs, you'll see this goes from white to dark gray. That's telling you that something's happening. When that goes back to white, your function is finished. Your program is done. So here's this program. It falls for 1 second, and after it has fallen from 1 second, starting at an initial height of 100 meters, it's at a position of 95 meters up in the ground, and it is descending with a speed of a velocity of minus 9.8. This particular program displays both my numerical answer and my analytical answer. And we'll go through all the lines of the code to understand what it's doing. The question from Kayla was, will the indicator go back to white even when the function is incorrect? Yes, it will. So if we put an error into the code, in there. I'm going to type in the line, this is a mistake, right inside, and it will tell me that that's a syntax error, but I goes back to white right again. So I have to fix those things all the way through. So it will only stay black when it's actually doing something, not when it's stopped. Okay. You probably know, I assume you know, but maybe not. Computers are binary, which means everything internal to a computer is either a 0 or a 1, an on or an off, an up or a down. Electrical signal is high voltage, low voltage. That's all that it knows. Internally, the only thing that a computer can register is whether or not a value is on or off, true or false, 1 or 0. We call those things bit. Binary digits, bits. The number 13, if you remember doing this from either math or computer science, is if I want to take 13 in binary 1101, is written in base 2. That is, each one of these numbers, this is 2 to the 3, this is the 2 to the 2, this is the 2 to the 1, this is the 2 to the 0. Fortunately, it has been a long time since we've actually had to program in base 2. There used to be a time, but it predates me, and it predates, I believe, everyone in the room by quite a bit. We get to work other things, but this is what the computer understands. Computer languages translate memory references and variable names and function names from letters and words and base 10 numbers into this base 2 representation. Cassandra asked the question, does Jupyter require manual indenting after the define function? No. Jupyter does a lot of nice things for you. If you start typing in DEF space function name and then round brackets, then colon, and hit return, it will automatically do the indent for you to be helpful. If you don't want to indent, then you press the delete key or backspace to make it go away. I'll point out that Python is a case-sensitive language. There's a difference between a capital T and a lowercase t. You can use any letter or digit or underscore you like for a variable name. Variables have to start with letters or underscores. There's a difference between the two, but they can have numbers inside the name. If you've programmed before, you've done any kind of programming, you'll be familiar with the concept of data types. That is, all variables aren't the same thing. There are different kinds of variables out there. Python also has data types. So when I create variables, I can create a variable like n equals the value of 10. Y naught is equal to the value of 10.0. Inert is a variable equal to the value of true. And a food is a variable equal to something called cheese. I've just invented 4 variables. If I execute that line, so I've now executed that block, what I've done is I've given you 4 examples of what are called primitive data types. An int, a float, a bool, and a str. Full form, we say that n10 is of class integer. An int is an integer. Negative numbers, zeros, positive numbers, but there's no decimal. Floating point numbers, or floats, are ones that have decimal places. It allows you to talk about things like 10.4 or 10.242 or whatever. A bool is a special kind of variable that represents what's called a Boolean. Boolean, as in George Boole or Boolean algebra, values are only one of 2 states, true or false. In Python, true and false are keywords, capital T true and capital F false all the way through. The final primitive data type which comes up is strings. Strings all the way through can put anything you want inside. You actually have some choice on how you want to use a string. You can either use single quotes or double quotes. It does not matter. The reason for having those 2 things is so that Python allows you to do these kind of things. So here are 2 strings. This is the string cheeses, where an apostrophe is part of the string, and double quotes are on the outside. And this is a string where we wanted double quotes on the inside, so we use single quotes on the outside. There's no special type for single character bytes. Use whatever you like, just be consistent all the way through. I tend to use double quotes, but it doesn't really matter. You have flexibility and choice. Okay, so we talked about steps all the way through. So now we have some data types. What can we do with these things? I want to talk about the assignment operator. What this is a line of code that makes a variable equal to something, assigns it in memory. What a variable is something in the computer's memory, and we have an identifier or a name we're giving to that location of memory. That's what a variable is. So when I have a line like x equals 10, what I'm doing is saying, dear computer, please take the number 10 and hold on to it for me and put it somewhere in memory. When I ask for it again, I'm going to use the identifier x to know about it. X will represent where in memory this thing happens to be. That's very convoluted, that's long, so we just say we assign x equals 10. It's putting a value in the memory. Assignments are not equalities. So it allows you to do things like this. X is equal to x plus 1. How could x equal x plus 1? That's mathematically impossible. If that was an equality sign, then we've just proved that 0 equals 1. And the solution here is, in Python, this is not equality. This is not an equals. It's an assignment operator. What we're saying is, take the current value of x, the value of 1, figure out whatever that sum is, 10 plus 1 is 11, and assign that value to x. So this is an assignment operator. The content on the right becomes assigned to the value in memory represented by x on the left-hand side. There are some more complications, but that's basically the idea. It's not an equality, it's an assignment. So there we go, I can add 1. This basically gives you a calculator all the way through. If you ever do calculations, using Jupyter or Python is really nice for doing math. Just you get to see it, it's like a visual calculator all the way through. A statement in a computer language is a sentence. That is a complete thought. Sentences, if we call that a statement, are made up of pieces. The pieces are typically called expressions. This is an expression. So this statement is made up of an expression and a statement. An expression is like a phrase in a sentence all the way through. We tend to make more interesting expressions by combining things together with what are called operators. So equals is an operator, plus is an operator. Python will automatically worry about data types for you. So if you've got a value like 11 and you add to it a floating point number, it will automatically interpret that 11 as 11.0 and do the right thing. You do not need to actually change over the value of any of these things on your own. One of the things about doing Jupyter notebooks is you notice that we don't always have to do a print. The very last expression in any notebook cell is always displayed automatically. So in any cell, the last expression, if it has a value, is displayed. If you have multiple values, multiple expressions in a cell, only the last one is displayed. And assignments, these kind of things, they don't have an expression. This is an expression, but the whole thing doesn't have an expression. Okay, so that all being the background. In running a program, we want to initialize some variables. This is going to explain what our program's going to do. So here are the variables that I'm going to introduce. Y equals 0 is the initial position. V0 is the initial velocity. I'm going to set a time counter equal to 0. I'm going to set a time step equal to 100th. I'm going to start with y and v being equal to their initial value, and I'm going to set a variable equal to the gravitational field. These variables, their types, are being chosen automatically. We don't need to worry about that. You can't have a variable that's defined that doesn't point to anything, but you do have this context of a none. You can have a variable which is referring to nothing, and that's often used in the language in special cases. A question just came by. Does that mean that if using a value was generated before, it has to be called / invoked in Jupyter? I'm not entirely sure I understand the nature of that question. Used before. Does it have to be used? No, it doesn't have to be used. You have to define it before you use it. If I just start and I jump out here and I say, print the value of this brand new variable, I don't know, blueberry, it's going to give me an error because it doesn't yet know what blueberry happens to be. If I give blueberry a string, then it can do something with it. So you have to define things before you use them. So Kayla, if there's more I can help with that, please let me know. Okay, so we've got the variables. What we're going to do with these variables is we're going to put them into a for loop. That is, we're going to string them up and iterate through the Euler algorithm. Loops have this block structure, similar to functions, where indentation, white space, is important. You'll notice how after a for loop, there's a colon, just like for functions. You need to have 4 spaces here, and that tells you that everything in this block is inside this loop. It means that this will happen once, twice, 3 times, 4 times, 5 times, and going from 0 up to 99. These lines, these expressions, this is the Euler algorithm, which we discussed before. This is just the rule that says take the old value of y, the old value, calculate an expression, and assign that to y to update it. That's the idea. We come up with these 2 lines by working out, potentially in paper, pencil and paper, what the algorithm happens to be. These loops go until some condition has been reached. So in a for loop, the condition is n takes on every value in this range. In a range, n starts at 0, and then takes on the value of 1, and then takes on the value of 2, 3, 4, 5, all the way up to, but not including, 100. So what that means is n takes on the value of 0, 1, 2, 3, all the way up to 99. I'll remind you that there is a more general form. In general, range has a start, a stop, and a step. So if you wanted to, you could start at 1. If you wanted to, you could step by multiples of 2 or multiples of 5. You could go as far as you want with these things. But that's the basic way of iterating through or stepping through some sequence. Again, note that where this loop ends is where I no longer am indenting. So indenting means the beginning of a loop or a block. Outdenting, stopping indenting, is the end of it all the way through. One of the things to check if you have a mistake is just to make sure your indenting is right. And again, so this code, if I made that mistake, this would happen 100 times, this would happen once. Now all 3 are going to happen all the way through. If my indenting is wrong, I will get this word called indentation error. It says, I don't know what you mean. This doesn't make any sense. So these red things are errors that we have to try and figure out. There's an indentation error right there. I don't know why you indented. That's what Python is trying to tell me. Okay, question. If we need to save these data for falling ball or recalling this as function, what should we do? We'll get there. I'll explain a pattern on how we're going to keep a history of these things as we go. Name y is not defined. Oh, this is common. This is so common. So here's an example of an error. It's telling me, I don't know what y is. How are you going to make me have y plus something when I don't know what y is? That's what the error is. The reason, as I scroll back up, you see this block of code? See how I haven't run it yet? That happens so often. Now it's been run. Now this will work. That's life. Skipping, jumping ahead. When it's all one program, you don't notice it. But when you do in these blocks, this happens from time to time. Okay, so we've now run our model. Again, indentation is a part of the language. There's no way around it. Some people love it and some people hate it. It's just what it is. I find it easier to read, so I like it, but I understand if you're like, I want my braces, because some people just like it. When the program ends, at the very end of the program, we display some results with the print function. So if you look back to the main program, it has these parts. It has an initialization section. It has a section which actually solves the numerical problem. And then it has a section which involves a bunch of print statements. Let's talk about those now. Print is a way of making something display to the screen. You print something, and whatever is in the round brackets is what gets printed. So I can print a string. That's pretty boring. And what, of course, gets printed is what's ever inside. Whatever string is inside here, that's what gets printed. Often what you want to do is you want to embed a number inside a string. And so to do that, I'm going to recommend using the format method. The format method is an operator on a string. What it does is it takes a string. So there's a string. A string has quotes. It has the words final, time, equals, and then these parentheses. These curly brackets are inside the string. And what format does is it takes whatever the value is of that variable and substitutes that right here. So this is how we can embed a value inside of a string. It's called a string formatter. Okay? So the final time after running this model is 1.000000007. And hold on, we'll talk about why we get that particular result. Multiple variables can be formatted together. This is where the format tool becomes useful. If you wanted to say y equals something and v equals something, maybe you have position and velocity, you can format two things, the first one and the second one, all the way together. So when we run this program, the final position is 95.148999997, and the final velocity is given. Both y and v are floating point numbers. The floating point is this dot. It means this dot is going to float somewhere in there. And internally, everything is a binary number. The computer does not have a decimal point inside of it. What it does is it has a way of representing floating points as binary numbers, and it does this with a convention or a standard called the IEEE 754 standard. Effectively, what it does is it takes any number you like, and rewrites it in, like scientific notation, leading part to some exponent. It reserves so many bytes or so many bits for representing the exponent, and so many bits for representing this part all the way through. There's only so many bits you can use, so there's only certain numbers you can exactly represent in this system. In a binary fraction representation, and of course this is true for decimal fractions as well, only certain numbers can be represented exactly. Right? What I mean by that? Well, like in fractions, okay, we'll do it this way. We'll start with a simple example. So in binary, what do you think 0.1 plus 0.2 should be? Okay, so without writing the code, we're just going to do it in our heads. 0.1, okay, 0.1, 2, okay, add them together. So what should I get when I run this thing? That's not exactly what I would have guessed, or I think you would have guessed, but that's what you get when you're doing floating point arithmetic on a modern computer. We're sort of good that we've at least standardized. There was a time when different computers, different manufacturers of computers would have a different answer for this last little bit. The standard of IEEE 754 agrees on which way we're going to represent these numbers. The reason it happens is because computers, using binary floating point, cannot accurately represent the number 0.1, 0.2, or 0.3 at all. Now, this might seem a bit strange, going, well, it's totally fine. I can do it, no problem. I can just write it down. I can write it down as 3/10 or whatever, and you're fine. But of course, there are numbers in floating point. In a base 10 system, I can't represent exactly either, right? Like this number right here. What's its floating point representation in base 10? It's not what I have written down there. That's an approximation, right? 0.33333333. If I stop there, that is not 1/3. It's an approximation of 1/3. In a similar way, in base 2, 0.1 and 0.2 can be represented exactly with 64 bits. So the floating point system chooses numbers that are very, very close. Now in practice, this doesn't really matter. There are errors everywhere in our modeling. The error down there in the 17th decimal place makes this pretty small. So one of the ways we can get around that is rounding the numbers when we actually go to display them. This is what your calculator does. When you have a calculator, a typical 8-digit calculator, it may hold 10 or 15 digits in its memory, but when it actually shows you the answer, it's rounded it to the 8 characters you can see on the calculator. we can do the same thing with these string formatters. What we can do with a string formatter is inside these colon brackets, specify how to display that thing. We're going to format it, colon, as a 3 decimal precision floating point number. Basically, we're going to round this off, so I'm only looking at the first 3. This is a nice way of hiding that event, that oddity, and sidestepping it, but be aware it is real and there's no way around it. There's a whole bunch of string formatters to ensure that things are the right width, string formatters to ensure that you have leading zeros, string formatters to write things in exponential notation. Whatever you may want, there is a website for examples of string formats if you need them. Okay, this program is going to conclude by comparing the numerical result to the analytical result. That is, I'm going to calculate using these expressions what the actual analytical value is all the way through. There's a number of operators, as I talked about in Python. There are pluses and minuses. There are multiplication, which is what the asterisk is. Some other very common ones are division, modulus, which is the remainder after you divide by an integer. All mathematics in most programming languages, and especially in Python, follow an order of precedence. I don't remember which one you would have learned, but basically the one that says bracket first and then exponents and then multiplication and then addition in that sort of order. That's handled as well. So even though this line says y naught plus v naught times t, the way it's actually evaluated is this part gets evaluated first, then this part gets evaluated, then it all gets evaluated together. So Python respects order of operations. If you do need to do a different kind of order of operations, there are parentheses. And finally, we can just display it. Run the code, don't forget to run the code, to compare the different values. Okay, so all of that is just like a tour into Python going, well, what can I do with it? You can do code, you can do math, you can do functions, you can write things out. That's like 80% of like lots of programming languages total. You can do stuff with just those constructs of loops and assignments of variables and expressions. You can go crazy with that. I want you to notice that we run this model. We ran it for 1 second of real time, 100 steps. The numerical answer and the analytic answer are not, it's not right. It's close, but it's not right. After 1 second, the exact numerical answer, the exact analytical answer is 95.1. But this algorithm is giving 95.149. Okay, so you've had me talking for like 45 minutes plus, 50 minutes plus. How about you do something now? So what I'm going to get you to do is I'm going to get you to run this application for different time steps delta t. And answer the question for yourself, do the numerical results become better as delta t is being smaller? And try and figure out a good value of delta t where the error is small. And try and figure out at what time the ball should hit the ground, right? So this is a big problem. A ball from 100 meters, when will it hit the ground? Below is the exact same code. I've removed some of the functions so you can just run it and play with it. And what I want you to do is go through the exercise of changing this and changing this to try and figure out how long it takes all the way through. So what we're trying to do is figure out dt, number of iterations, and final time. Kyle is going to walk around the room and try and help you guys to do this. Because I'm here today, I also will do this, but in practice, I won't be. Send me a text or drop a text what your best guesses are here. Iterations and final. And as soon as I see some numbers popping up in that chat box, I realize that if you're not using Zoom, you can't respond, but some will. That'll give me an indication that we can move on. And if there's any more questions, please let me know. Okay, everyone, let's dive back into this here. So I have got 2 responses that said used a range of 1,000 and the numerical and analytical results was the same. And then someone else says, use this in range to get this. Okay, so these were two answers. Okay, so here we go. I'm going to say that what we determined was dt equals 0.12345. Okay, and range 1, 2, 3, 1, 2, 3. Okay, someone has said that is the appropriate fix. So if you haven't done it already, we'll change this to being, is it 1,000,000? So difficult to read numbers. Okay, I'm gonna go with 1,000,000. 1, 2, 3, 1, 2, 3. Here's a cool little Python thing. That's legal syntax, because it's really hard to read that otherwise. 1, 2, 3, 4. 1, 2, 3, 4. Okay, so let's run this program. Aha, okay, so this is pretty good. No, it's not pretty good. 1, 2, 3, 4.
For the range.
100,000 for the range. 100. Yay! Okay, this is fantastic. So after 100,000 steps, this object has fallen to a height of 95.1 meters off the ground. We're not done. At approximately what time does the ball hit the ground at y equals 0? No one's answered this question yet. So we're still searching. So that's a great time step. That seems to be accurate, but you have to go a lot more steps to be able to actually hit the ground all the way through, right? So let's up this number. Let's go with 500,000 steps. Am I at the ground yet? I'm past the ground. Let's go with 400,000 steps. Oh, I'm almost to the ground. Let's go with 450,000 times steps. I'm getting closer to the ground. Let's go 455,000 times steps. Oh, I'm a bit past the ground. Okay. Oh, but now I've got some more error in my model. Oh, a range of 450,000 is close. I agree. It is close. It is definitely close. Okay. We're going to put this down as our answer. So we'll say 450,000. That answers the question. Okay, so this is one ways of using a model, right? I wanted to figure out what the final time was. And the hope was you found this to be a slightly annoying process because no one would actually ever do it this way, right? The idea of having to go through the code, change a number, and do it. It's annoying for a couple of different reasons. One is you have to change the number and rerun it. At least when you're running Python code, this is pretty fast. It's annoying because as soon as you change AT, to get the same final time, you have to automatically increase the size. And finally, there's no way of figuring out before you run the model how long you should run it for to make sure it hits the ground. So there's ways of changing this model code to be able to answer these kind of questions more directly. One of the ways is to not use a for loop. Rather than saying I want this model to run for 450,000 steps, there's other ways of doing loops in Python. And one of the things we can do is we can change the code so that rather than using a for loop, we use a while loop so that the program will stop whenever the ball hits the ground. There was a question that was asked in the chat. Is this a trial and error process in Jupyter to generate the answer, or is something we should calculate on paper before putting in Jupyter? This is a trial and error process in Jupyter. This was a test by playing. Put numbers in, see what happened. That was the goal here. Okay, so let's do the next thing here. This program will be better if instead of a for loop, you try a while loop. So what I want you to do is I want you to go back to this program and change a certain line . That one, so that you're dealing with a while loop instead. And what you're going to find is it's going to be a lot easier to figure out what value of dt is needed and the final time all the way through. Because there's different kinds of doing loops. So you try that all the way through and see if someone can give me a more precise estimate of the final time. It's 4.5-ish, but let's see if we can do better. Okay, so we'll just come back and we'll finish off this example. Sarah was the first one to give me an answer in the chat. I almost agree. We'll change while y is greater than 0, and we can see that the final time does turn out to be 4.5157. The numerical and analytical ones are not exactly right. So if I make y just slightly smaller, no, they're almost there. Can make it even smaller. The thing about running this program is we make our time steps smaller. You can see that it takes longer to actually run. That's because you need to take more steps. Accuracy will increase, but running time will also increase. So there's a trade-off between these kind of things. So it's about how accurate you want to be able to go. To 4 decimal places? Oh, that's interesting. I wonder if we're all doing giant loops right now on this one little tiny computer. There we go. Sarah wins. But we didn't need that many time steps. Okay, so there's a piece of code. This is a piece of code you now can modify, iterate on, change. You understand now all the lines in it all the way through. Is there a way of changing the step size without trial and error? Yes, we will get to that in lecture 3, where I've got ways of looping through different steps, where we have interactive widgets for playing with those steps. And of course, there's ways of solving for what that step should be. Run the program until the time step is small enough. It's all about putting these programs together in certain ways. I'll leave it with this particular exercise. So this is the second thing I'll put on assignment number 1. Here is a piece of code, or rather, here is a mathematical expression. It's a series. I want you to sum this series, as in figure out 1 plus 1 over 2 squared plus 1 over 3 squared plus 1 over 4 squared, and not add it up. So write some code and figure out what the program should be to n equals 10, and work on how many values of n do you need so that n is accurate to within 2 decimal places. Then look at what happens if you look at the error between the convergence, basically how much different it is, not just for 2 decimal places, but 3 decimal places or 6 decimal places, and then play out with something else. So this is something we'll put on assignment number 1 as a intro to Python programming question, just to give you some practice in doing that. This lecture is filling off with some text that I got from another book. Basically, it's just some notes on programming style. Typically, we want to use comments, not too many comments. We want our names to be meaningful. It's okay to be verbose. So when you are programming, the reason we have programming languages is for you and for me. It's for the humans involved. The computer does not care. The computer would be totally fine with a whole bunch of languages which were awful for us to have to deal with. We write programs in Python to be readable for us. So if it takes you an extra 2 or 3 lines to write down what you want to do, take the extra 2 or 3 lines. Rather than trying to get the entire thing on 1 line, go ahead and space it out. Here's an example of what I mean. So here's a piece of code where I calculate the analytical value of y, the analytical value of v, and then I print it all out. Would this have been an allowable line? Would this have worked? Okay, so can you see how that block of code, this does exactly the same thing as this does? This is just harder to read. And the nature about code is you spend some time writing it. but code is written once and read many, many times. Code tends to live a lot longer than you think it does. It really doesn't make it run any faster or slower to do this, but it's far easier for you or someone else to read it. So we try and make our code as readable as possible, ideally readable enough that you don't really need comments at all. If you have good, clear code, there's no need for comments. This program probably only needs a comment saying what it does in total, and maybe the fact that we're using the Euler algorithm. And beyond that, I wouldn't put any more comments in this program than that. This program simulates a falling ball using the Euler algorithm. And that's it for comments. You wouldn't need any more than that all the way through. And finally, I've got a little bit of text here on testing and how you check whether or not things are right. And I will leave this lecture with a suggestion to go and take a look at the textbook for the course, read through chapter 2.1, and read at a skimming level, section 2.2, but it said don't get hung off on any of the Java. This course isn't going to include the Java. I've tried to sort of replicate all the main points inside this lecture. And we will continue on our next lecture, making these ball applications more verbose. We'll add in widgets, we'll add in graphs, we'll add in the ability to automatically choose the time step. We'll look at better program structure, and we'll make that ball bounce and do some more interesting things. So before I stop the recording today, are there any other questions that you want to give me on the chat? I said I'm still in the room for a few minutes afterwards if it's one-on-one stuff, but any remaining questions? Okay, well, thanks very much, and we'll see you next time.